So now we are going to derive the formula or the equation of general heat diffusion equation or general heat equation or general conduction equation. So let's start with that. So general heat equation or heat conduction equation or heat diffusion equation. These are the three names, but we'll say general heat equation. So for deriving the equation, the first basic assumption is we are assuming that there is no bulk motion within the control volume. No bulk motion. Within control volume. So let's make a control volume. So we have a cube or a cuboid control volume. Okay, and there are three directions. So x, we have y, and z. Okay, so whatever heat rate is coming in is called as qx from that phase. Whatever is coming out over here is called as qx plus dx. So this length is dx length, this breadth is dy, and the height, this height is called as dz. So accordingly, in the same way, whatever is coming in from this bottom phase is called as qz, what is coming out from the top phase is called as qz plus dz, q dot, the rate, and whatever is coming in from the front face is called as q dot y, whatever is coming out from the behind face, backward face, is called as q dot y plus dy. Okay. So we start from the basic conservation of energy principle, which is E dot in minus E dot out plus E dot gen is equal to the change in energy of the system with time. Okay, and the change in energy of the system will be given as the heat generation will be given as this. Sorry, the heat generation will be given as q dot small q dot gen. So that is per volume into dx into dy into dz. So that is the differential volume of the control volume. Okay, and this q dot which I used is heat generation per unit volume. So we have used normalized heat generation per unit volume. Now the q in is the q dot x, q dot y, and q dot z. Those are the three terms which will come in q dot in. What will come in q dot out will be q dot y plus dy, q dot x plus dx, q dot z plus dz. That's what come in q out. Q gen we have already defined over here, and the change in the change in energy of the system, I'll define that right now. So the energy of the system is mCp delta T. Okay, that's the energy of the system, and now that's energy of the system changing with time. So del E by del T, it should be del over here because there are multiple factors, there are multiple x, y, z and time, so it should be partial differentials. So now del E by del T will be equal to, I'm changing mass with rho V, and rho V will be rho dV because we have differential volume. and dv is dx into dy into dz. That's mean rho into dx into dy into dz into cp del t by del t, right? So we have got our change in system. So we have got all the terms. Now just we need to put those terms on our equation. One more clarification, one thing we can do is the q dot x will be written as minus k into a into del t by del x. The area over here, that is a bit complex and you just need to make a note of it. The q dot x will be k into del t by del x. The area will be this area, that means the height of that area is dz and the breadth of that area is dy. That means it is dz into dy. That means whatever, if here the partial differential is with respect to x, or if we are finding the q dot in x direction, the areas are y and z. That's mean if I am finding y, the things will be dx into dz. That means x and z are over here, y is over here. We can verify it over here also. The y, it is entering from the front face. That means the length is x and the height is dz. That's what we have achieved over here. So using this, we can put all the terms which are over there, and what we'll get is what I'm writing right now. So we'll get these things are coming over here. The q dots. So minus del by del x into minus k dy dz del t by del x into dx, and accordingly the terms for y, accordingly the terms for z, here the dy will come, plus the term for q dot gen dx dy dz is equal to rho dx dy dz cp del t by del t. Okay, so we have got this equation, and simplifying this, what I'll get is I'll get k del square t upon del x square plus del square t upon del y square plus del square t upon del z square plus q dot gen is equal to rho cp del t by del t. Coming from over here to over here, we have made one assumption. What's that assumption is? We have taken the k from inside the differential to outside the differential. Otherwise the k was inside the differential of this spatial coordinate. When we are taking it out, that means we are assuming that the k is not changing with direction. That is, it is constant at all places. If that's not correct, the k cannot be brought out. That's the only difference. In that case, this equation will be final. If the k is constant, that means this equation can be simplified, and now this equation is our final equation. And I'm just writing this again by taking k at the bottom. So if I take this k at the bottom, what I'll get is this term q dot gen will have k in the denominator and rho cp will have k in the denominator. So let me define one another constant, rho cp by k. I'll take this as alpha, which is called as thermal diffusivity. Alpha is termed as thermal diffusivity. Remember this. So now my final equation will be del square t upon del x square plus del square t upon del y square plus del square t upon del z square is equal to plus q dot gen by k plus is equal to 1 by alpha, so this should be defined as k upon rho cp, that's rho t by del t. Okay, so that's the final equation. This is the final, final equation for general heat equation, right? So we have derived this. In next video we will look at some more properties or more facts about the thermal diffusivity. Okay, thank you.